Hello everyone. Welcome to today's online webinar of Asiagraphics. It's our great honor to invite Professor Jianmin Zheng from Nanyang Technology University and Professor Yi Liao from Zhejiang University. In the first part, Professor Jianmin Zheng will give the talk followed by question and answer, and then Professor Yi Liao will give the second talk. At the beginning, let's go to the first part. And let me introduce Professor Zheng. He's a professor in the School of Computer Science and Engineering at Nanyang Technology University. He received his bachelor degree and PhD from Zhejiang University. His research areas include computer graphics, geometry modeling, visualization, and AI for design and 3D printing. One of his famous work is to design the T-spline technology that has been widely used in CAD and CAE industry. Today, he will talk about 3D shape parsing from point cloud. Okay, let's welcome.
Okay, thank you, Zheng, for the introduction. So good evening, everyone. So I'm thankful to Prof. Ligang Liu for inviting me. So I'm very happy to have this opportunity to share my research via the AG webinar, right? So the title of my talk is 3D shape parsing from point clouds. So the title actually indicates the talk is about 3D point cloud, especially shape represented by 3D point clouds and shape representations, and also shape parsing or understanding. So to me, these topics are quite interesting and exciting. So they actually contain some fundamental research issues, research problems, but meanwhile, they have some practical value. So in this talk, I will share some of my research in these topics. And particularly, so I will present two recent work accepted by ICCV last year and ECCV this year. So this work was done by my PhD student, Zheng, and they are also the outcome of this collaboration with Professor Cai Jianfei at Monash University. Excuse me. So when we talk about the shape representations, it's related to the digital 3D models. Right? So as a type of the media data, as digital 3D models actually have wide applications. And in early times, so those models are used in like a CAD/CAM industry. And later on, 3D models appeared in like animations, movies, and games, right? And scientific research, visualizations, and also engineering simulations. And nowadays, 3D models are also very important, for example, for metaverse applications, and also digital twins. Okay, so the digital model of the real-world objects are of great interest. Actually, they are something reality computing focuses on. So look at this picture on the left side. So it's a side of the Haw Villa. Haw Villa is a park in Singapore exhibiting some Chinese and Asian culture. So on the request by the Travel and Tourism Board of Singapore, we digitize this site. So we create a lot of point clouds, and then we process point clouds to create a virtual model. So here we can see, okay, nowadays they're relatively easy to obtain or generate point clouds, and the point clouds are unstructured. So they do not provide those semantic or high-level information explicitly. So, however, I mean, in many applications, high-level representations and high-level understandings are required because they help us to understand the shape, understand the thing, and also benefit many high-level processes and analysis. So there's a lot of research done in these directions and try to create the high-level representation from low-level representation, such as a point cloud. So the first step, like I say, okay, 3D reconstructions, right? So 3D reconstruction converts the point cloud into the mesh. Right? So compared to point cloud, the mesh are more compact and more structured. At least the mesh and conveying information of how vertices are connected with each other. But the mesh themselves are still low-level representations. They do not explicitly provide high-level information or semantic information either. So this slide actually shows the work done by Professor Zheng. So the next step, say, go to the shape decomposition. And actually, this is also the Zheng's work, actually part of his PhD thesis. So here, okay, shape decomposition partition the objects into meaningful parts. Actually, this is hard. So we like to each part, okay, match the human shape perception. So this conveys some high-level information or high-level representation. This helps us understand shape and benefit the high-level editing, for example, example-based editing. And in industry, actually, there are some special requirements for high-level representations. For example, in building and construction industry. So BIM is a model containing some high-level informations. So in a recent project with Junon, so we are required to create a BIM from scans. Actually, this is a quite challenging problem, especially to construct a BIM model from scan automatically. Right? Junon is a local company in Singapore. So in another project, I undertook, that's the Virtual Singapore project. So we are required to create a model in CTGM format. And the CTGM format is a file widely used in GIS applications. It contains several levels of details, so representing the different levels of the informations. So we developed some tools or semi-automatic tools which can convert like the point cloud or mesh into like a CTGML, like a LOD2 or LOD3. Okay, those are some research we did in the past. Right? So my current interest falls in the following problem. So now if we are giving objects represented by point cloud, so how can we convert that into high-level representations? So this actually is quite a fundamental problem, right? So, well, so the definition of the high-level representation is quite subjective and depends on the application, depends on the scenario. Right? So we propose some criteria for this. For example, okay, high-level representation should be compact, right? Not like a point cloud, there's a lot of points. So we should have a more compact representation for the shape. And the second is the shape should be intuitive and we can understand each component. And the representation should be easy for further editing. And moreover, we like high-level representation. It's easy for learning process. So those are some basic requirements we want high-level representation to have. So like checking some literature of the geometric modeling, and we find the CSG tree might be a good high-level representation for this purpose. So CSG actually stands for solid constructive solid geometry. It's a popular and also fundamental representation for geometric model, especially for solid model. Right? So it's compact and editable and also interpretable. Right? So in CSG, the object is represented by some simple shape, such as like here, like a box, sphere, a cylinder in this slide. Right? So you can see those simple shapes can be defined by only a few parameters. So it's easy to edit. Right? But on the other hand, you can find that this CSG tree, right, could have different structure. The structure is quite dynamic, depending on the scenario, depending on the object. So this might make it difficult for learning process. So let's check the fundamental elements of CSG. Right? It has two components. The first one is primitives. So here I'm usually like a box, cylinder, sphere, and cones are the primitives for CSG. and these serve as a building blocks. And the second element of CSG is Boolean operations, including intersection, union, and difference. So those primitive objects are recursively combined by Boolean operations to form more and more complicated shapes. So eventually find a single object. So that's a CSG representations. So as I mentioned, the CSG tree might not suitable for learning, or it's at least difficult for learning. So to get rid of this dynamic nature of CSG trees, so our basic idea is to flatten the CSG tree. Flatten the CSG tree. So we try to group the same Boolean operation together, for example, all the intersections together. So in this way, and eventually we come up with a fixed 3-layer structure. So we call the CSG-Stump. So CSG-Stump has 3 layers. The first layer is called a complement layer. So it's applied to or corresponding to the primitive object. And the information tell, okay, whether this primitive remains there or should we use the complement of this primitive. The second layer is called the intersection layer. So intersection layer tells, okay, which node in the complement layer should be included in the intersection process. And in the third layer is a union layer. So it tells, okay, which node in the intersection layer, the second layer, should be included in the union process. So eventually used to define the final object. So in that case, you can say each layer has a very clear rule, and also the structure is fixed. So we call it like learning friendly. Okay, here's an example. We have a mechanical part, right? This mechanical part can be represented by a CSG tree or CSG-Stump. Right? And both representation involve 8 primitive objects, like 2 boxes and 5 cylinders and 1 cone. Right? So now we like to propose a question. So okay, can both representations of both structure equivalent? So that is okay. Can both representations be converted to each other? Right. So this is actually important. So the answer is yes, and this can be proved mathematically. So the conversion from like CSG-Stump to CSG tree is obvious. Right. So we just, if you understand the property of those union and difference, those Boolean operations. And the backwards conversion from CSG tree to CSG-Stump can be proved by induction. So let's look at the base case of where there are only 2 primitive objects like P1 and P2. Right? So for example, when we do the intersection, P1 intersection P2, and this is from CSG trees. But we can formally represent this guy as a CSG-Stump form. Right? So we introduce an empty set, we use a cassette for this whole space, right? So then you can say, okay, so the primitive level, you have P1, P2, and also empty set and the whole space. Then we do complement level, we don't do anything. Then do the intersection, second level, and third level to the union, right? So similar analysis can apply to union and the difference. So then, okay, by induction, you can prove, yes, I mean, any CSG tree can be converted into CSG-Stump. So that means both representations are equivalent. So that means CSG-Stump can represent any CSG tree. Okay, now to realize the concept of CSG-Stump, right, we need to design some appropriate data structure. So we have seen that the CSG has 2 parts, primitives and Boolean operations. Right? So for primitives, we use some parameter called intrinsic parameters, extrinsic parameters to represent the primitive shapes. For example, a box, right? Intrinsic parameters are 3 edge lengths in its standard position. So in standard position, that means the center of the box at the origin, the edges are aligned with those XYZ axes. Right? Similarly for other primitives, extrinsic parameters include the translation and rotation transformations, and they make the standard primitive object in the required location and in required orientation to form the final shape. For, like, say, connections or Boolean operations, so we introduce 3 binary matrices to encode these connection layers. In particular, for the first layer, for complementary layers, so we use a matrix WC. Like WC has a size of 1 by k, and k is the number of the primitive objects. Okay, so this binary matrix, the entry has a value either 0 or 1. Right? So 0 means, okay, we don't perform complementary, so the primitive object remains there. But if the entry value is 1, that means, okay, we use the complementary to the primitive object. Okay, the second layer, so we use another matrix, WI. I stand for intersection. Right? So WI is for the intersection layer, and the matrix has a size dimension of k by c. Right? So the rows correspond to the number of the node in the first layer, or the primitive object, and the columns correspond to the number we set up for this intersection layers. Right? So that is okay for each element in this matrix. If the value is 1, then we'll say, okay, so the object, the node in the first layer should be included in the intersection process. But if say, okay, the value is 0, entry value is 0, that means the corresponding entry is not included. And the third matrix is WU. WU is for union. Right? So the size is C by 1, and C corresponds to each node in the second layer, intersection layer. Right? Similarly, the value 1 represents the corresponding node should be included in the union operation, and 0 representing, okay, that node is not included. So in this way, so eventually, the CSG-Stump will store like the primitive object in terms of the intrinsic, extrinsic parameter value and 3 binary matrices. All right, so then we also need some ways to represent the object and each node in the CSG-Stump structure mathematically. So mathematical representation sometimes allow us to well formulate the various application problems and or do optimizations. Right? Considering that Boolean operations are involved in CSG-Stump, so it's convenient to introduce the occupancy function for the object representation. So actually, occupancy function is widely used recently in neural representation of the shapes. So here, for example, for particular object O, so we use O of P as the occupancy functions. So then for a point belonging to the object, so O of P equal 1. So otherwise, O of P equals 0. So this is easy to understand. Right? So in this way, so we can say for the empty set, so its occupancy function is identically 0. For the whole space, its occupancy function is identically 1. Okay, then for each node in the first layer, complementary layers, right? So we will say, okay, we use Fi to denote the occupancy function for that node. I stand for the ith entry. So in this matrix, we store value 1 or 0. 0 means the corresponding node don't perform complement, right? So that means the primitive object remains there. So then you look at these expressions. So if the entry value is 0, that means second term vanish. The first term gives you OI or OP. That's the occupancy function for this primitive object. But in case, okay, a particular entry has a value 1, so then the first term vanish, and second term give you 1 minus OI. So that's the occupancy function for the complement to the primitive object. Similar for the second layer, the intersection layer, for each node, we use the SI to represent the occupancy functions, right? So S stands for the second layer. So I for the ith entry. So in the matrix, okay, so the I column are used to represent this node. Right? So for each entry in the ith column, so we tell, okay, the corresponding entries in the first layer will be included or not. For example, okay, if a particular value is 0, so then, so Wi will vanish, the second term will vanish, and the first term gives you a value 1, that's maximum value. And the maximum value 1 will be ignored later on due to the use of minimum. But if the entry value is 1, so the first term vanishes, second term gives you F, J, or P. That's an occupancy function for the node in the first layer. So that's something we want. Right? And also know that say in Boolean operation, the intersection can be achieved by the minimum function for the occupancy function. So that's reason here we use a minimum here. So for the third layer, there's only a single node called root node, right? So we use a P as the occupancy function for the root node. So T stands for the third layer, right? And actually T actually represents the occupancy function for the final object, overall object. So the matrix for the third layer actually is a column vector or matrix of C by 1, right? So you can say entry has a value 1 or 0. So 1 represents the corresponding node in second layer will be included in the union process. So the occupancy function of the corresponding node in the second layer will be included. But if the value is 0, so then this expression will give you 0. So 0 will be ignored due to the use of maximum function, because union function can be achieved by maximum function. So that's the reason here we use the maximum function. Okay, so those are mathematical functions which can be used to represent each object and also each node in the CSG-Stump structure. Okay, so with all this ready, so we can formulate our 3D shape parsing problem, right? So the CSG-Stump, you can see, is quite flexible and fundamental representations. So now our problem is like this way. So the input is a shape given by point cloud. And we want to reconstruct the CSG-Stump representations. So that is, so we output a set of primitive shapes. So by its parameter value. And the 3 connection matrices tell how those shapes are combined, right? So this by nature actually is an inverse problem, right? Generally quite challenging. So the first approach, okay, we propose to use a binary programming. So that involves 3 steps, right? The first step, actually, we use some existing method, like the occupancy network proposed in CVPR 2019. So this allows us to generate a target shape occupancy function. So for point cloud, we create the target shape occupancy function, and this serves as a target function. Then we run ransack to predict the primitives. So how many primitive objects we need, and what are those primitive objects? So then you can say, okay, to build the CSG-Stump, what do we need? Just to find the connection layers. So the connection matrices can be found by find the solution of this minimization problem, right? So here in this minimization problem, the variables are 3 binary matrices, WC, WI, and WU. Right? All the entries are just by number, either 0 or 1. So that's the reason we call this a binary programming. Okay. So we like this predict the occupancy function for the final shape, match the targeted occupancy function as much as possible. So this is a minimization problem. Right? So, but in general, you can say, okay, this predict the occupancy function actually is a composite function. It's quite complicated. Right? So we use this global optimization to solve this problem. Right? So this simplifies our job. So it works pretty well in general, especially for simple shapes with just a small number of those primitive objects. So especially if the number of the primitive objects is less than, say, like 10, it works quite well, right? As shown in these two examples, there are only 5 primitive objects. But if for objects is very complicated, its shape is very complicated, or there's a lot of primitive objects, then this approach will take a long time and might diverge, might not converge. Right? So that's the reason, okay, we turn to seeking another approach using like machine learning to find a solution. So for that purpose, we propose CSG-Stump Net. Right? So here is a basic architecture of this net, very relatively quite simple network architecture. So we use some traditional like net backbone to encode the point cloud, input the point cloud into some latency feature vector. So then we design MLP to decode the latent vector into primitive head and connecting head. So primitive head just tell, okay, how many primitives and those parameters, intrinsic parameter value and also extrinsic parameter value. And a connection head actually to recover those 3 connection matrices, right? So for those primitive objects, based on those parameters, actually we like to compute the occupancy function. So that eventually we can compare with the target occupancy function as a loss, right? To learn this process. This is a unsupervised learning. And to make the process more stable, there's some tricks we can play here, right? So especially to define the occupancy functions. So usually it's a kind of binary, right? So it's not, differentiable. So we take some, follow some idea of existing work. We compute a signed distance function, right? So or construct a signed distance field and then use a sigma function to convert a signed distance field into occupancy function. So in this way, can make the algorithm more reliable. And similarly, okay, there's some other trick you can play, like the loss function, you can add some terms, and also the maximum minimum function can be replaced by the relaxed version using, for example, the soft max, right? And also for the connection matrices, the entries are just binary, but we can relax this to, like, say, to find some soft value between 0 and 1. Use also use some other way to do that. And eventually, then you just do a threshold to that, and this can make this learning process more reliable. Okay, here's some examples. Okay, some experiments. We performed on this data set called the shape net. So the shape net was produced by research group at Princeton University and Stanford University. The data set contains a few models which contain quite a lot rich information. So we compare our method with the CSG net, right? So you can see visual effects, and here also visualize our result. So we also compare with the other state arts in this type, like the VP stand for method assembling with the volume primitives, and SQ stand for the method using super quadrics, right? And US CSG, just as I said, is an unsupervised CSG net, right? So eventually, we will also do this comparison quantitatively. So, and here we measure the error using chamfer distance. And you can find the CSG-Stump actually gives a minimum error in average. So, and more evaluation is presented in our paper. So we like evaluate using other metric. But overall, we can say, okay, the performance of CSG-Stump actually is quite good, or at least on par on the state art, and or even better than the performance of state art. And also we can say, okay, so eventually the result is quite compact, involve only a few primitive objects. But here I just show the second layer, so not so many elements we need in the intersection layer. But in the primitive layer, we need more primitives, but still not so many. So eventually the representation is quite compact. And then moreover, okay, since eventually you output the object in can say CSG-like representation, it's compatible to existing 3D software. For example, you can use like Fusion 360, the Autodesk product, or you can use the open SCD software to do the further editing. This is just one example, right? So this editing is high level, right? So a few parameters you can adjust, and compared to point cloud, this is much easy to understand and more intuitive and flexible. So the implementation of this CSG-Stump can be found in my students' GitHub. Nice. Okay, so those are some interesting structure, especially so personally, I like this CSG-Stump structure. It's quite fundamental and simple. So then, okay, what's next? So we like to explore something beyond CSG, right? So we can say, just as I said, the CSG-Stump actually give a very simple description for Boolean operations. So that means for some application require Boolean operations, not necessarily CSG. So CSG-Stump might be also used for that application. But meanwhile, okay, in traditional CSG, the primitive objects are quite simple, just as I listed earlier, like the sphere, the box, the cylinder. But in real situation, we can actually extend and generalize those primitives to more general situation, right? So this actually gives us some hints to do the further exploration, especially to check this actual modeling process. For example, okay, in many 3D applications, and people actually do the modeling using a process called a sketch, and then do the extrusion. This is quite an intuitive process, widely used, especially in industry, 3D industry, right? So here you do the sketch, draw some circles, straight lines, or freeform curve like B-splines or Beziers. Then do the extrusions and create very nice shapes, right? So we like to, to reverse engineer this kind of things. And this tells us compact representation, still high level representation, but meanwhile, we also know the modeling process. So our basic idea here is, given point cloud, so we try to figure out the sketch, the 2D sketch on the sketching plane, then do the extrusion, and that form one part of this reconstruction shape. Right? So that's the basic idea. So eventually, we can reuse the framework we use in CSG-Stump. So that involves 4 components. The first one, we still use encode-decode architecture to generate required parameters for this extrusion parts, right? But this can be done using like a dynamic graphic CNN network, and to do the encoding, and for decoder we still use MLP. Right? Then we need some representation for sketch. How can we represent these extrusion shapes? Right. So that's something we have to explore. Right. But meanwhile, for the new primitive object, we should have some way to compute the occupancy. So that's something we also need to develop. So after that, you already have quite a few extrusion shapes. We have to assemble them. So, but this can be done by CSG-Stump. So then you can say, in this framework, so the first, last, we already know. So then we pay attention to the middle 2 components. Right? So then you say, what about the sketch on the plane? Right? So here you have to trade off the complexity and the reliability. Right? So we'll find, sketch should be a closed curve, right? And should have no self-intersection, because otherwise it makes the situation very complicated. But meanwhile, in real application, especially CAD industry, So the shape is smooth, or at least the piecewise smooth, right? And should have the capability of modeling like freeform curves, circle, and polygon. So in this sense, okay, so we propose some ways, some strategy. For example, we use a polar form to achieve this to realize this closed requirement and no self-intersection, and use rational Bezier to represent the sketch. Right? So in particular, say eventually a closed curve is formed by several segments, for example, n segments, and each segment is a special rational Bezier curve. In particular, we use a cubic Bezier curve defined by 4 control points and 4 weights. But special, we just fix the first last weight to be 1. So eventually we have only 2 inner weights. Right? So this is a special rational Bezier curve. So in that case, we reduce the number of the parameters, because if you have too many parameters, it's difficult to learn. Right? Okay, then we just say, okay, distribute each segment evenly along the origin to form a closed shape. Right? So in that case, for each segment, we have a central angle of 2 pi over capital N. Right? So then for each Bezier curve, the control points will represent by polar coordinates rather than Cartesian coordinates. So we have rho as the radial coordinates and alpha I as the polar angle. Right? So then, furthermore, we define the polar angle in some special way for one segment. For example, okay, you have 4 control points. So if the first point has a polar angle alpha 0, then the second control point, its polar angle is alpha 0 plus theta. Similarly, okay, so the last point, the polar angle is fixed because we already know the central angle for this segment. Then the P2, the polar angle is the alpha 3 minus theta. Then what's theta? Theta is a specially designed angle. It's computed like this way. Then you may ask, okay, how you come up with this complicated angle? Actually, we do some reverse engineering. So this angle is specially designed to achieve required property. So I will show that in this way, we can reduce the number of the parameters. Or now what you can say for those 4 control points, all those polar angles are fixed. So we only have the radial coordinates, right? So there are only 4 radial coordinates plus 2 inner weights, 6 scalar number. So then, okay, such sketch curve has the following properties, which actually sets our requirement. For example, they form a star shape, right? So since the angles are distributed in a special way, so this closed curve form a star shape. Each point can be viewed by the center. And also 2 adjacent curves can meet with the C1 condition if those control points are specially designed. A weight and a control point satisfy those conditions. Geometrically, that means those 3 points are collinear, right? But of course, if the condition is not satisfied, then those 2 curve segments meet with only C0 continuity. This actually reduces the number of the freedom. So there's some constraint on those parameters, right? And you can say for each segment, if all the control points are collinear, like on same line, then we can say this curve is a line segment. And this is due to the well-known convex hull property of the rational Bezier curve. Right? In particular, since we're interested in the circle, so you can say we can prove that. Actually, you can find the proof in our appendix of the paper. So if you set the radial coordinates properly, and also set the weights properly in this way that involve the angle theta, then we can prove the rational Bezier curve is a circular, arc. So in that case, we can represent the circle exactly. Right? So those are some representation for our sketch curves. Right? So then, okay, so with the curve, just as I said, to compute the occupancy function, we have to compute some sign distance function. So usually for rational Bezier curve, it's difficult to do that. And we propose a general approach, numerical approach. We sample all those points on the curve, right? Give a numerical way, and then give a numerical to compute the sign distance function, and right side show this sign distance field for all the points. You can see this field actually quite smooth, right? So now the issue is, okay, for this extrusion object in 3D space, how can we find the distance function? So for example, point P here, so I'd like to find the sign distance function with respect to this extrusion part. Okay, that's complicated. However, we use extrinsic parameter rotation matrix R and the translation vector T. We can transform P back to the standard coordinate system P prime. Then, okay, compute the relative sign distance function with respect to this standard extrusion. So the extrusion defined by the sketch curve on the XY plane and also extrusion height h. So we find and formulate the formula in 3 functions. Eventually, we have explicit representations, like using minimum maximum functions. But eventually, minimum maximum function can be replaced by relaxed version. So this can simplify our learning process. So eventually, we have similar network architecture. So input a point cloud, then we do the encoding into the latent vector. Then we do decode and decode into the shape head and also decode into the connection head. So then during learning process, and we can learn the extrusion part, the extrusion parameters, intrinsic parameters, those are rational Bayesian definition, and also extrinsic parameters like rotation translations. So those are some results, okay, by our method. So looks just as you can see, actually the performance is pretty good and even better than previous CSG-Stump in terms of the chamfer distance. Right? And also we do some evaluation of this 2D sketch and give the very good approximation for the signed distance field if the sampling point is large enough. Like usually, okay, for each curve, we choose 100 or 200 sample points. That will be enough. If we increase, then you will reduce the error, but not so significantly. But that will increase the computation time. But if the sampling number is very small, then the accuracy will be sacrificed. Okay, so then you can see some results, and the results are in high level because in Bayesian representation. So it provides a control points a way to do the further editing. So we can input the output of network into some 3D system. Then we have Bayesian control polygon do the further editing. So this kind of editing is high level. Right? So this is just illustration of our process. So you can also find the code in my students' GitHub site. So then, okay, so the network can figure out those sketches for the particular object. Then also can estimate the extrinsic parameters, the rotation and translation, and also the extrusion height. So now we assemble all these extrusion parts to form the final shape. Right? So this is according to those connection matrices. Okay, due to time, I just skip over there, just come to the summary. So in this talk, so I show some work about 3D shape parsing. Right? It's a quite interesting task and quite useful in practice and a fundamental problem because it covers some high-level components and representations for 3D shape, especially for 3D shape initially represented by low-level data like a point cloud. So this talk also presents a CSG-Stump structure, very simple structure, which is very suitable for describing Boolean operations. and also present extrude net, which can reverse engineer underlying constituent and modern components, and also the extrusion process for 3D shapes. So I would say, okay, those work are not necessarily best, right? Or I mean, so just some initial attempt in these topics. So there's still a lot of room for further improvement, and still a lot of space for further explorations, right? So that means more research is needed. So I look forward to more research and new research outcomes in near future. Right.
Okay.
Okay, so then I will end. Right.
Okay. So many thanks for Professor Zheng's wonderful talk and very good work. So in the next, we go to the question and answer session. So there are several questions, and okay, the first question is that in the first work, are they basic geometry elements fixed or not? If they are fixed, is it possible to learn the basic geometry elements in the CSG-Stump framework?
So usually, like say, okay, in I mean traditional CSG method, right? CSG representations. So the primitive objects are usually fixed, like say, okay, use spheres, box, and cylinders, cones. Those are common ones. But in some applications, people can extend it to like super quadrics or some more complicated situation. So in our experiments, we just choose 4. But of course, I mean, theoretically, you can include more things. But it's difficult to automatically introduce that. Or now, when we train this CSG-Stump network, so then you have to fix that. Because otherwise, currently the network is not so smart to introduce the new primitive object. Because otherwise, it's difficult to know, okay, which one should be treated as a primitive object, right?
Mm-hmm. Okay, so I think this question is somehow like a dictionary learning. We can say that the basic elements are the dictionary, right? And we in this work we adopt this CSG to like a union or some other strategy to compose them. But in the dictionary learning framework, if the basic elements can be optimized. So, for example, if some indoor scenes, there are some object, the shape is quite is not regular. So if we use this this sphere or something like this, maybe it's not the best, right?
Yeah, I think that's possible. So actually, the second work actually is kind of like in this direction. So we replace the primitive object. But now, see, although we don't call them the primitive object, but we call them so extruded parts. But in principle, extruded parts actually serve as a primitive object, right? And on the other hand, sometimes you can also use, as you mentioned, say, deep learning. So you have some pre-processes, do some initial analysis from the input data, and come up with some relatively complicated shape as a primitive, as some work like say presented by people from this Stanford University. So they use some like the convex combination of the half plane to form the primitive objects. So then, yeah, so that case, so you can use some way to learn some primitive shapes first, or basic shape first. Then you can plug in this into our this CSG-Stump net to do that. That's also possible, but I don't know whether that's a good idea or not. Really, it's a trade-off, right? But just as I said, in the traditional CAD industry, usually the primitives are just those are relatively simple, like sphere, cylinder, cone, box. Those are sufficient for general situation.
Okay. So the second question is a general question. So how do you think the the linear network-based method and the linear representation will help the CAD and the CAE related problems. So traditional CAD and CAE is like spline or something like this, and proposing a detailed lot of quality work in this field. And recently, this linear-based method or linear representation, like a linear implicit function, and also the CSG-Stump network is a new way to for geometry modeling, right? So do you have any suggestions on this research direction?
Well, actually, I have no clear answer to this question, but my thinking like this one, say, okay, so those linear representations, right, actually are quite interesting, especially of interest in the community of computer vision, right? But when you come to like the CAD industry, in those industry which require very high precision representations, so far maybe still there's some problems. But say for the very complicated shapes or things, we want to come up with some more abstract or compact representation. But relatively, the precision might not be so important. Then this linear representation might be quite interesting and useful.
Yes. Mm-hmm. Okay.
And it also provides some high level, I mean, meaning like semantics there.
Okay. Okay, so there are no more questions. And okay, let's thank Professor Zheng's wonderful talk. Okay.
Okay, thank you. Yeah.